Welcome to the deep dive. So if you're right in the middle of your AMT general course, you know just how much information is coming at you. It's a lot.
It really is.
Our goal today is, well, maybe a bit of a shortcut. We want to cut through some of that noise and really focus on the core physics, the mechanical principles. These are the things that honestly underpin every single maintenance task you'll ever do.
Exactly right. For an aviation tech, physics isn't just abstract theory. It's the tool that tells you how things fly, how an engine works. But more than that, it lets you quantify it.
Quantify. What do you mean by that exactly?
It means you can put numbers to it, you can calculate, predict, troubleshoot. We're talking piston engines, gas turbines, you name it. Physics gives you the math.
So instead of just saying, wow, that engine's powerful, you can actually calculate like the exact pounds of thrust coming out of a big GE90.
Precisely. That's the difference. But before we can start calculating anything, we kind of need to set the ground rules, the basic principles. Let's start with matter itself.
Okay, matter. Sounds fundamental.
It is. Simply put, matter is anything that occupies space and, crucially, has mass. And the number one rule, the law of conservation of matter.
Matter can't be created or destroyed. I remember that one.
That's the one. So think about a long flight burning, say, thousands of pounds of jet fuel. That matter doesn't just disappear, does it?
No, it becomes exhaust gases, right?
Exactly. It changes form. Which brings us straight to a really critical point, one that trips people up all the time. The difference between mass and weight.
Ah, yes. Mass versus weight. Why is this so important for a technician to nail down?
Because they're fundamentally different things. Mass is the actual amount of stuff in an object, the atoms, the molecules. It's constant. It doesn't matter if you're on Earth or the moon.
Right, intrinsic quantity.
Right. Weight, though, weight is a force. It's specifically the pull of gravity on that mass. It changes depending on where you are.
So when we see astronauts floating around on the ISS, they're not really weightless. Is it more like they're constantly falling?
That's a perfect way to put it. They're in a state of perpetual freefall with the station. They absolutely still have mass, and gravity's still acting on them. It just looks like weightlessness.
Got it. Mass is always there.
Always. And speaking of mass, in the English system, which we use a lot in aviation maintenance, we have to deal with a slightly weird unit, the slug.
The slug? Always sounds a bit strange. Why do we need it? Why can't we just use pounds?
Well, it boils down to making Newton's second law of force equals mass times acceleration. FMA work nicely with our common units. If you measure force in pounds, you need a unit of mass that fits.
Okay.
So a slug is defined as the mass that accelerates at 1 foot per second squared when you push on it with 1 pound of force. And since Earth gravity pulls at about 32.2 feet per second squared.
Then an object weighing 32.2 pounds here on Earth must have a mass of exactly 1 slug.
You got it. It's the unit that connects weight, mass, and acceleration in the English system. It just makes the math consistent.
Okay, makes sense. Now moving from solid objects, what about fluids? Air, hydraulic fluid, fuel. How do we think about matter there? Density comes into play, right?
Absolutely. Density is just how much something weighs for a given volume. Weight per unit volume. Water is our usual benchmark, about 62.4 pounds per cubic foot.
But we don't usually calculate raw density for everything, do we? We often use specific gravity, SG.
We do. SG makes things simpler because it's a ratio. It compares a substance's density to a standard.
No units, just a number.
Exactly. For liquids and solids, we compare it to water. For gases, we compare it to air. It's super practical for maintenance.
And the classic example is checking a lead-acid battery with a hydrometer. How does SG tell us the battery's charge?
It's a direct indicator. When a battery discharges, the sulfuric acid gets used up, leaving more water behind in the electrolyte. Water is less dense than the acid solution.
So the electrolyte gets thinner, less dense.
Right. So when you put the hydrometer in, the float sinks lower. A reading around, say, 1.150 tells you it's pretty much discharged.
And if it's fully charged?
Then the electrolyte is dense with sulfuric acid, the float rides high, and you'll see a reading maybe between 1.275 and 1.31. That simple ratio tells you the battery's chemical state.
That's a great example of stored chemical energy, which leads us nicely into energy itself. We talk about 2 main types in aviation, right?
Broadly, yes. Potential energy, or PE, is stored energy. It can be energy of position, like lifting an airplane up on jacks. That's gravitational potential energy.
Or it can be chemical potential energy, like in fuel.
And that's a huge one. 1 pound of avgas holds about 18,900 BTU of heat energy. That translates to, wait for it, over 14 million foot-pounds of potential work. stored energy.
Wow. Okay, and when that stored energy gets released, when things start moving.
Then it becomes kinetic energy, KE, energy of motion. An airplane rolling for takeoff, spinning turbine blades, flowing fuel, that's all kinetic energy. The whole point of an engine is converting potential energy into useful kinetic energy.
And we measure that useful output as work.
Yes, but work has a very specific technical definition. It's force multiplied by distance. W equals F times D.
Simple formula. But there's a catch, isn't there?
A big one. For work to be done, the force has to actually overcome resistance and move that resistance through a measurable distance.
This is that classic physics example. If a couple of techs push with all their might against a plane that's stuck, maybe its brakes are set and it doesn't budge an inch.
Then, technically, even if they're sweating and exhausted, they've done zero work on the airplane. They've burned chemical energy in their muscles, sure, but no physical work was done on the object because distance was zero.
A tough lesson. But usually we are moving things, often against friction.
Right. Friction is the resistance we're usually fighting in maintenance. There's static friction, what you overcome to get something started.
Harder to start pushing than to keep it rolling.
Exactly. Then there's sliding friction, when surfaces rub.
Mm-hmm.
And usually the smallest is rolling friction, like with wheels.
So towing a big plane, say a 130,000-pound Boeing 737, doesn't require 130,000 pounds of force on the tow bar.
Not at all. You're mainly working against the rolling friction of the tires on the pavement, not lifting the plane's weight. So the tow bar force might only be something like 5,000 pounds to get it moving horizontally. You're overcoming a resistive force, which is much less than the total weight.
Okay, now if we consider how fast we do that work, that brings in another concept.
That's power. Power is the rate of doing work. It's work divided by time, or force times distance divided by time.
And the standard unit we use, especially for engines, is horsepower, HP.
Right. James Watt figured out a standard. 1 horsepower is defined as doing 33,000 foot-pounds of work in 1 minute.
Let's apply that. Say we need to lift a really heavy engine, like a GE90, maybe 19,000 pounds. We need to lift it 4 feet up to install it, and we want the hoist to do it in, say, 2 minutes.
Okay, let's run the numbers. 19,000 pounds times 4 feet is 76,000 foot-pounds of work.
Divided by 2 minutes gives 38,000 foot-pounds per minute.
Now, divide that by 33,000 to convert to horsepower. 38,000 divided by 33,000. It's by 1.15 horsepower.
Only 1.15 HP. That seems surprisingly low to lift such a massive engine.
It does, right? But it shows that most heavy lifting and maintenance isn't about raw speed or power. It's about using machines, hoists, gears, levers to gain mechanical advantage. We trade speed for force.
Which brings us to rotational force, or torque. This is super important when you're tightening bolts or dealing with engines.
Absolutely critical. And it's different from work. Work is force acting through a linear distance. Think foot-pounds or inch-pounds.
Okay.
Torque is a force acting along a lever arm or a radial distance, causing a twist or rotation. To keep them distinct, we invert the units. Pound-feet or pound-inches, usually pound-in or pound-ft for torque.
So inside an engine, if the combustion pushes down on a piston with 500 pounds of force and the crankshaft offset the lever arm is 4 inches.
Then you're generating 500 times 4, which is 2,000 pound-inches of torque. That twisting force is what turns the crankshaft and ultimately the propeller or fan. Torque gets things rotating. Work is the energy transferred over distance.
Got it. Torque is the twisting effort. And you mentioned machines help us apply force or torque effectively. How simple are these machines, fundamentally?
Amazingly simple. You know, every complex machine, from a watch to a landing gear mechanism, is really just based on combinations of 2 fundamental principles.
Yeah.
The lever and the inclined plane.
Just 2. Okay, let's talk levers. There are different classes, right?
3 classes based on where the fulcrum, the pivot point, the resistance, the load, and the effort, the force you apply, are.
First class.
Fulcrum's in the middle. Think of a seesaw or using a crowbar to pry something up. You push down on one end, the load goes up on the other.
Second class.
Resistance is in the middle, between the fulcrum and the effort. A wheelbarrow is the classic example. You lift the handles, effort, at one end, the wheel is the fulcrum at the other, and the load sits in between. This always gives you a force advantage.
Meaning you lift a heavy load with less effort, but you have to move the handles further.
Exactly. You trade distance for force.
And third class.
Effort is in the middle, between the fulcrum and the resistance. Think about your own forearm lifting something, or maybe the retraction actuator on some landing gear. The actuator pushes somewhere in the middle of the gear leg.
So what's the advantage there? It sounds like you need more effort.
You do lose force advantage, but you gain speed and distance at the end where the resistance is. Great for things that need to move quickly through a large arc, like retracting gear or flight control sometimes.
And this trade-off, force versus distance, is quantified by mechanical advantage, MA.
Right. MA is simply the force you get out divided by the force you put in. If a lever system gives you a 5-to-1 mechanical advantage, MAA equals 5, it means you can lift 50 pounds with only 10 pounds of effort.
But there's always a but.
The but is work conservation. That 50-pound weight will only move 1/5 of the distance that your 10-pound effort moves. You can't get something for nothing. Force gain means distance loss and vice versa.
That principle seems absolutely fundamental in hydraulics, too. Trading distance for massive force multiplication.
Precisely. Hydraulics run on Pascal's law. It's the bedrock. It states that if you apply pressure to a confined fluid, like hydraulic oil in a sealed system,
That pressure gets transmitted equally everywhere in all directions, and it acts perpendicular to the container walls.
you've got it. And the math is beautifully simple. Force equals pressure times area. F equals PXA.
So let's walk through that classic two-piston example. Small input piston, large output piston.
Okay. Say you push with just 5 pounds of force on a small input piston that has an area of only half a square inch, 0.5 inches.
Pressure is force divided by area, so 5 pounds, 0.5 inches is equal 10 pounds per square inch, 10 psi.
Right. Now, Pascal says that 10 psi is transmitted everywhere in that closed system, including acting on a much larger output piston, maybe one with an area of 5 square inches.
So the force on that output piston is pressure times area, 10 psi times 5-inch in switch, which equals 50 pounds.
Exactly. You put 5 pounds in, you got 50 pounds out. That hydraulic system has a mechanical advantage of 10. That's how we move heavy flight controls or landing gear with relatively small inputs.
But again, the work conservation rule applies, right? That big 50-pound output piston won't move as far as the small input piston.
Absolutely not. If the MA is 10, the output piston only moves 1/10 the distance of the input piston. You gain force, you lose distance. Always that trade-off.
Makes sense. Now, what about fluids that aren't confined, fluids in motion, like air flowing over a wing or through an engine? That brings in another principle.
That takes us to Bernoulli's principle. Daniel Bernoulli figured out that for a fluid in motion, liquid or gas, where its speed increases, its internal static pressure decreases. Faster flow, lower pressure.
The classic application is lift generation on a wing. But where else does an AMT see this directly? Maybe in a carburetor.
A float-type carburetor is a perfect example. It uses a venturi that's a deliberately narrowed section in the air intake passage.
So as the air gets squeezed through that narrow throat,
Its velocity has to increase significantly. Bernoulli says faster flow means lower pressure, so you get this low pressure zone right in the throat of the venturi.
and that lower pressure sucks fuel out from the float bowl into the airstream.
Precisely. It's the pressure difference that draws the fuel in and mixes it with the air. Simple, elegant application of fluid dynamics.
Understanding moving air naturally leads us into aerodynamics and the big picture forces on an airplane.
The famous 4. Lift, weight, thrust, and drag. All are forces, all measured in pounds. And the aircraft's state climbing, descending, accelerating, cruising depends entirely on how these forces balance out.
If thrust is greater than drag, the airplane accelerates.
If lift is greater than weight, it climbs. If they're all balanced, it's in steady, level flight.
Lift is probably the most talked about and maybe the most complex to explain fully. It's not just one thing causing it.
That's true. It's really a combination of effects. Bernoulli plays a big part that the air flowing faster over the curved top surface of the wing creates lower pressure there compared to the bottom surface, resulting in an upward pressure difference.
But that's not the whole story.
No. Newton's third law for every action there's an equal and opposite reaction is just as important. The wing is shaped and angled, angle of attack, to deflect a large mass of air downwards.
Action. Pushing air down.
Reaction. The air pushes the wing up. Both Bernoulli's pressure difference and Newton's reaction force contribute to the total lift.
And to withstand these forces, lift, weight, engine thrust, landing, impacts the aircraft structure has to handle enormous stress. Why do parts eventually fail?
They fail when the stress applied exceeds the material's strength. And structures experience stress in 5 main ways.
Okay, let's list them. Tension.
Tension is a pulling force, trying to stretch apart. Think of a cable or the lower skin of a wing in flight.
Compression.
The opposite, a squeezing or crushing force, like the force on a rivet being installed or the upper skin of the wing in flight.
Then torsion.
That's twisting. It's actually a combination of tension and compression acting on diagonal planes within the part. A propeller shaft or an engine drive shaft experiences huge torsional stress.
Okay, what's next? Bending.
Bending is what happens to a wing spar, for example. The top surface gets compressed, the bottom surface gets tensioned. It's a combination stress.
And the last one, shear.
Shear is like a cutting or slicing force. Imagine two plates bolted together, pulling in opposite directions. The bolt experiences shear stress right across its diameter, trying to cut it in half, like scissors cutting paper.
Understanding where these stresses concentrate is crucial for inspections, right? Looking for cracks or deformation.
Absolutely vital. Knowing the type of stress helps you know what kind of failure signs to look for.
And all these forces and the aircraft's structure ultimately allow us to control the aircraft around its center of gravity, the CG. We need to understand the axes of rotation.
Right. 3 axes, all intersecting at the CG. First, the vertical axis, running top to bottom. Rotation around this is yaw.
Controlled by the rudder.
Correct. Then, the lateral axis, running wingtip to wingtip. Rotation around this is pitch, nose up or down.
Controlled by the elevators or stabilator.
Yep. And finally, the longitudinal axis, running nose to tail. Rotation around this is roll, banking left or right.
Controlled by the ailerons or sometimes spoilers. And the relationship between where the CG is and where the aerodynamic forces act is critical for stability.
Hugely critical. If you load the aircraft incorrectly and the CG moves too far forward or aft, it can become unstable or require excessive control inputs, making it unsafe or inefficient to fly. Proper weight and balance is pure physics application.
Wow, okay, that really covers the spectrum, from basic matter and forces all the way to flight controls and stress. It all connects back to these fundamental physics principles you learn in the general course.
It really does. You can trace almost any maintenance procedure or system operation back to these core ideas. Pascal's law in hydraulics, Bernoulli in the carburetor, Newton's laws for flight and engine thrust, stress analysis for structures. It's all there.
So, to wrap up, maybe one final concept that ties a lot of this together: pressure, temperature, density, performance.
A really important one for pilots and technicians alike is density altitude. We know air gets less dense as you go higher, right?
Pressure drops.
But temperature also plays a huge role. Density altitude isn't just your physical altitude, it's the altitude the air feels like it's at, performance-wise, after you correct the standard pressure altitude for the actual temperature.
So on a hot day, even at sea level, the air is thinner than standard.
Exactly. Hot air is less dense. So on a hot day, the density altitude might be thousands of feet higher than the actual field elevation.
And that means?
That means worse performance. Less dense air means less lift from the wings, less air mass going into the engine, so less power, and you need a longer takeoff roll. It can seriously impact safety if it's not accounted for. It combines pressure and temperature effects directly on performance.
That's a critical practical application. And just to leave people with something truly mind-bending about physics at the extremes, think about aerodynamic heating.
Oh, yeah, like on the SR-71 Blackbird?
Cruising up there at Mach 3.5, 3.5 times the speed of sound. The friction from just air molecules rushing past the skin.
It generated incredible heat. Skin temperatures ranged from maybe 450 degrees Fahrenheit on cooler parts up to over 1,000 degrees Fahrenheit on leading edges and around the engines.
1,000 degrees F, just from air friction.
Which is why they couldn't build it out of aluminum like most planes. Aluminum loses its strength way below those temperatures. They had to use exotic, expensive titanium alloys for almost the entire airframe just to withstand the heat stress caused by extreme speed.
That really drives home why understanding these physical principles, friction, heat, stress, materials, isn't just academic. It's literally what keeps airplanes together and performing safely.
Couldn't have said it better myself. It's the foundation.
Go deep, stay curious, and thanks for joining us on The Deep Dive.